All right, so the last bit for today is to talk about descriptive versus prescriptive uses of signatures and how this design here is going to help us find some bugs that we couldn't find before. So the um, ordered signature, if you think about it, could this be used in the way that we talked about using signatures last week, where we said that a signature describes everything that you know about an unknown type, that the everything that the client knows about an unknown type? Well, no, because for example, this signature just says there is a type T and you can compare two T's. It doesn't give you a way to make any T's, which is what we want because like down here, the way to make int less than T's is numbers, right? We want to be able to compare numbers, right? We'd like to be able to write int less than dot compare of 2 and 3 and get less, or int greater than compare of 2 and 3 and get greater, or string less than of compare of A and B and get less, but string less than dot compare of 1 and 2, we get a type error because ints are not the same as strings. Okay, so we want to be able to use the comparison function on any old values of type int or string that we happen to run across in the rest of our program. We don't want to be tied to just ones provided by this particular module. So that's what's called a descriptive use of a signature, which is that we describe a type that has some operations sort of non-exhaustively, or among other operations, and so on. So what we're going to do is we're just going to describe that, hey, there's a type T and it's got this comparison function. That's what dictionaries need as input. They need to know that there is this type and it has a comparison function. There might be lots of other stuff about that type that's true too. The particular fact that our implementation of dictionaries as binary search trees uses is just that it has a comparison function. Okay, so that's a descriptive use of a signature. A prescriptive use of a signature is like saying there's a type with some operations, but that's all of them. So it's exhaustive rather than non-exhaustive. So when we think about dictionaries, we do want to think of the dictionary signature as saying there's a type of dictionaries and the only things you can ever do with it are empty and insert and lookup. And the reason is this idea of representation invariance that we talked about in Wednesday's videos, which is that if the tree is sorted, and whenever you empty creates a sorted tree and insert into a sorted tree gives you a sorted tree, then nobody else can break the invariant that the tree is sorted. In particular, if you ever see a tree that's not sorted, then you know to go find that bug right in the code for this tree dict module, not somewhere else. And so the for that reason, we sometimes want types where it's sort of closed off and we say, this is it. The only things you can do are these things. And which isn't to say that you might never want some future operation. For example, in the homework, you're going to be looking at making a merge operation for dictionaries. But the way that you'll do that is to go and put another operation in the signature. There's now a val merge, blah, 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 and then you go implement it, right? So it's like a change to the signature to expose a new operation if you've got a prescriptive or a and that's it use of a signature. Okay, so conceptually, there's some times when signatures are just describing true facts about a type or some types, and there's sometimes when the signature is saying that's all you know about the type. And in particular, the dictionary module has both examples going on because key.t, the type in the key structure, is supposed to be treated descriptively, whereas the dictionary type itself is supposed to be treated prescriptively. And we can already see that. For example, down here, I can say, what's my dictionary named? String dict dot key dot compare. I can apply that to a couple of strings that I cough up, and that works. So down here, the idea is that the descriptively, we remember what the types are. So for example, we know that for our int less than dot t is equal to int tree dict dot key dot t is all int, and we know that string less than dot t is equal to sdict dot key dot t, which is string. And so we can just use any old operations on things that work on ints or strings on those types. In particular, we can just write down a string and that has type int less than dot t. But prescriptively, we're supposed to have the idea of a new type where the only thing we know is the stuff in the signature. So in particular, what that means is that if I do a sdict.insert, so let's say I make a little dictionary, which is int treedict.empty, and then maybe I do an int treedict.insert into int treedict.empty, and I'm going to put in, okay, 2 mapping to A. Okay, so that makes a dictionary. Now, what happens if I do an sdict.insert into D2 with the string A maps to 2? I get a type error. And why is that? Well, sdict is a dictionary whose keys are strings. Int dict is a dictionary whose keys are integers. And if you think about the type of keys, that means that trees, that means that the keys here stored in one of them have an int here, and the keys in the other have a string here. And so it doesn't even make sense to like think about doing an insert into an int keyed dictionary with a string key because, well, when I compare two things, right? Like the key.compare would be the one sitting in the dictionary that you're doing the insert for, which is strings. But then if you find an int there, then it's going to try to compare an int and a string, and that's undefined, right? That would crash. The comparison function doesn't know what to do if it gets an int on the one side and a string on the other. And so, right, we want that to crash. Well, that would crash, and so we want it to be a type error. And the way in which we get a type error is that sdict.dict is not the same as int treedict.dict. Okay, and these are different types. That's what we want. And then similarly, well, to go back to that example that we had before, int treedict.dict is supposed to not be the same as backwards int treedict.dict. And this was the example we did in the first video segment of, well, if you insert, if the tree is sorted one way and then you use the wrong comparison function to do your lookups, then you don't find the values that you expect to find because you're looking up on the wrong sides. And so we also want those to be different types. Now, in this case, it happens to be the case that if you just kind of looked at it, then a tree for ints with the less than comparison function and ints where the trees where the keys are ints with the greater than comparison function would actually be the same type. And so the code would work, but conceptually it's wrong. We don't want that lookup to accidentally return none because we looked down the wrong side because we used the wrong comparison function. Instead, what we want is that we actually are prevented from doing this, and it says that there's an error. And so we also want different types there. Okay, and so we're actually getting different types. So for example, if I do int tree dict dot lookup of my d up there, which is created using the backward stuff of 2, then I get a type error that says an int tree dict dot dict is different than a backwards int tree dict dot dict. I won't even let you run this lookup. It's not going to do what you want. And so we're finding the bug early by getting a compile error rather than it going down the wrong sides of the tree at some point when you use the code at runtime. Okay, so how are we doing this? Well, the idea, like why does SML give you an error message here? The idea is that every use of a data type produces a new type that you know nothing else about. And 2, every time you use a functor, you get a new use of the data type. So when we run int tree dict equals tree dict dot int less than, it's as if we took int less than, copied it right here in place of the k, and then loaded all of those declarations. In particular, we're loading this data type declaration for key being int less than. When we run tree dict of int greater than, we do the same thing. We take the greater than and we put it where the k is, and then we load it again. And so the effect of that is that it's like loading the tree declaration twice for different types, right? So if I say structure key equals int less than, and then I load this data type declaration, then I get a data type of trees. And it's now a data type of trees where the keys are ints, but it's kind of tied to that particular time when I loaded that data type declaration. So if I then say structure keys is int greater than, and then I load the same type of trees again, I get another type of trees where the keys are ints, but the keys are different, even though the type of trees is really the same type in structure. It's treated as a different instance of the type, and so it won't be treated as the same type from the perspective of the type checker as the previous one. Okay, so what that means is that we get that int tree dict is not the same as backwards int tree dict, and so everything's all sorted out. And every time you make a dictionary, you get a new type of dictionaries that's different from the dictionaries from all of the previous instantiations of them with different key types. Okay, so every use of a data type produces a new type that you know nothing else about, besides its constructors, maybe let's say. And every time you use a functor, you get a new data type. Okay, so the rule then is that if you want to treat a type prescriptively, which means that the client can only do what's in the signature, then define it to be a data type and don't put the constructors in the signature. So if in my piece of code, I make a data type like tree, and I don't tell you about the word empty, and I don't tell you about the word node, then there's no way, even though you know what the tree type is in some sense, like even though the client knows that it's the dictionaries are defined to be this tree type over there, there's no way to write down code that opens up the tree, because to open up a value of type tree, you need to do a case analysis and pattern match it as empty or node. And there's no way to construct a tree, because to construct a tree, you need to write down an empty or node. So all you can do then is the empty and the insert and the lookup coming from the signature. So the way that we'll use this semester to make types abstract, that is, we'll call this an abstract type or an unknown type. The way we'll use to make types abstract is that you put a type in the signature. In the implementation, you define it to be a data type, and you don't tell anyone about the data type constructors. So we'll see an example of this in lab tomorrow, and then we'll go over it a little bit more in a video on Wednesday. Okay, talk to you later.